So a Euclidean domain is essentially an integral domain in which you can do division. So more formally, it is an integral domain R which comes equipped with a norm function. It takes the non-zero elements of the ring to natural numbers. So this n is natural numbers. So it takes all elements A of the ring R, and you can write this A as QB plus R. So you can think of R as a remainder. So this QB and R lie in the ring R. So there are two things which R can take. So either R can be 0, or the norm of R has to be less than the norm of B. So some examples. So first examples is integers. You can do our standard division in integers, and the norm of say n an integer is just absolute value of n. So again, in this f of x, where f is a field, so it's a ring of polynomials with coefficients in a field. Here also you can do division, the long division of polynomials. Here again the norm of f, where f is a polynomial with coefficients in f of x. So f, this is a polynomial, this lies in this. So here the norm is degree of f for f in here. So the first proposition we want to talk about is that Euclidean domain is a principal ideal domain. So before we prove this, let us see a corollary. So now we have given an example. So say if f is a field, then this is a principal ideal domain, because this f of x is a Euclidean domain, and this proposition says that Euclidean domain is a principal ideal domain. So this becomes a principal ideal domain. So now by the properties in principal ideal domain, we know that the polynomials in this polynomial ring with coefficients in a field f, this can be factorized uniquely into primes, and the primes and irreducibles are the same in a PID. So in a PID, primes are equal to irreducible, and we show the unique factorization also happening in a PID. So let us start with the proof of this proposition. So you start with an ideal I in our ring R, and we have to show that this ideal is principal, that is, it is generated by a single element. So if this ideal is 0, then it is just generated by 0, and we are done. There's nothing else to do. Generated by a single element which is 0. Now if I is non-zero, then there is some non-zero element B lying in I, such that you choose this B in I such that d of B is minimal. So for a non-zero ideal, you choose an element B in I which is minimal, and this B is not 0. So this B is not 0. So the norm of B is minimal among all elements of I, and we will now show that this ideal I is generated by this single element B. So now pick any element other than B in the ideal I. So then you can write this A as QB plus R, where this R lies in ring R. So basically I'm just copying this down. So there are two cases now. Either R is 0. So if R is 0, then obviously A lies in the ideal generated by B, and we are done. Now if R is not 0, then you have this condition: d of R is less than d of B. d of R is less than d of B. But we had made the choice that d of B is minimal among all elements of I. So this cannot hold by our choice. So cannot hold. And that is precisely because this R you can write as A minus QB. So R also lies in I, because A is in I, B is in I. So R also lies in I, and Q is an element of R, but these two are in I, so this is in I. So R is in I, but as we said before, that the minimal norm of I is supplied by B, and you cannot have this because that will lead to a contradiction. So the only case we are left with is that R is 0, so A has to lie in the ideal generated by B. So more importantly, we have this relationship: Euclidean domains, strict inclusion into PIDs, which have a strict inclusion into unique factorization domain. So more about this and about particular examples, so that this inclusion is strict. This you can find in Dummett and Foote abstract algebra. So you should possibly see for more examples here in Dummett and Foote. So that will give you this precise relationship with examples. So it is a good idea to now look at this book and see all the examples corresponding to UFD, PID and EDs.